Good. Happy Monday morning, everybody. That's a bit of a, what is that word when two things don't go together, like jumbo shrimp? But anyway, so let's see what we can do. What?
Oxymoron.
Thank you. Yes,
Happy Monday.
that's exactly right. Like, I had a counter class stuck in my head for some reason. I knew that wasn't right. All right, let's get going, you guys, and see what we can do. It is a beautiful Monday morning, though. You got to give it that. Sunny. It's supposed to be in the mid 70s today. It should be gorgeous. This week looks like it should be downright gorgeous as well. If anything, maybe a touch too hot, but it is late April, so go figure. So that's pretty cool. All right, so let me let my cat out. There you go. All right, here we go. The joys of teaching at home. So, yeah. Anyway, so moving on. Just reminded me of a story when I was teaching with, I think Jeremy, you might have been here for this. No, maybe not. But I was teaching at Gray's house. And they were fostering like 27, it wasn't, but it was like 12 foster kitties, and they were everywhere. These little 4-week-old, 5-week-old kitties. I think this was years ago, so this is probably before you, Jeremy, even. But they were everywhere. They were crawling up my leg. They were on the whiteboard. Every student had a kitty in its lap.
Maybe it was Kaya.
What?
Maybe it was Kaya. I think you started before me.
Yeah. No, it was, yeah. This is the first high school class actually that I did. That's right, way back when Maria Hunter and your brother was in that class. That's it. It was your brother, Ben. Your brother, Jeremy. Yeah, was in that class. Ask him about that. That was crazy. That was crazy. That's the craziest class I think I've ever taught. And I've taught some crazy classes. Anyway, that'll be on the final. So if just kidding. Okay, maybe an extra credit question. All right, anyway, so let's get moving here. So a couple things I want to do today. Deep breath. First off, no quiz. Hey. Second off, we're going to teach you a slightly new concept, but it's very easy compared to what we've been doing so far, and very, very important, something you need to know. So we're going to give you something called molarity. Talk about that. We're going to do a little bit more with acid and bases because I want to bring you guys to, there's a concept called titration and neutralization. Titration is actually a type of an experiment. Stick it up here a little bit today. Is actually a type of an experiment that you can do to find the concentration of an acid or a base if you don't know what it is. And I found a magnificent website that basically we're going to do a lab today based on this website. It's, I don't know if I'd say it's fun, but for what we've been doing so far in chemistry, it's fun. It's like the Disney World compared to what we, anyway, so other than having balloons explode on you at home, this is so good. So we'll do that today. And then kind of go with that. So kind of a nice, as far as new concepts and new learning goes, a nice easy day as far as that goes. But a lot of important stuff to give you today as well. So good. Yeah. So first off, let's talk about a concept called molarity. All right. So let me share my screen with you. Whoops, hold on. My screen up, get my whiteboard up here this morning. Monday morning blues. All right, yes. Please ask me 27 more questions about how I want to start this program. Okay, now. Okay. Now, molarity. Is a way to measure the concentration of a substance. Formula for molarity, usually big M, is equal to moles divided by liters. Now, sometimes it's not liters, sometimes it's other things, but it's certainly moles divided by volume is molarity. So it's how many moles are hanging out in how many liters. which would make sense, right? That would be molarity. If you put more stuff in there, there'd be more moles in that same amount of volume. So it would be a more concentrated solution of whatever it is you're talking about. If you had, let's say, 5 moles in a certain amount of liters, and you then increased it to 10 moles in that same amount of liters, you will have doubled the concentration of that substance. That's all there is to this. This was really very, very simple. It's just a way to measure the concentration of a substance. And this is vitally important because remember, concentration should kind of ring a bell for you, right? That was one of the things we talked about a couple of weeks back when we talked about reaction rates. And the higher the concentration of a substance, the more likely you are to have a reaction. So very often, especially in acid-base reactions, you're going to be talking about having a certain molarity, 1 m of HCl, 2 m's of NaOH, 0.725 m's of H2SO4, whatever it might be, right? Very, very common to have this measured out in moles, all right? In molarity, I should say. Notice your moles were back. Yay, moles. I know you were like, oh, we're not going to use those. We're not going to learn anything else with moles the rest of this year. Well, thankfully, that's not true. There it is again. So just do a couple of, excuse me, I'm sorry. A couple of very quick calculations, then we'll do something a little bit fun with this. So first off, very quick calculations. Oh, there's a new button on my screen. I've never seen that. Never seen that before. All right, anyway, so molarity, let's say you've got, make this very simple. Let's say you've got, there, so you can read it, 3 moles of hydrogen chloride, hydrochloric acid, in 4 liters of water. What's the molarity? In chat, please. If you guys are awake today. There you go. Leif, good. And first. Mackenzie, good. Good. Jeremy, good. Noah, good. Yep. James, good. Yeah, it's that easy, guys. I know you're looking for the trick. You're looking to, right now, this is that easy. I'm going to take it up a slight notch in a second, but it's
Jim?
that easy. Yeah.
And the canvas things, if we wanted to get it right without you looking over it, should we put a small m or a big M in? It's a big M, right? And you're going to most of the time put that in the answers. Then we should do that if we want to get it right before grading. It's really just a mental health thing, you know?
Yeah, I know. I hate that. I hate the way that works. I get that. Yep. Yeah, it'll normally be like 1 m and the M will have no space between it and a capital M. Yep. Although lately what I've been trying to do is give a whole variety of options, which somehow people never guess the options that I've given anyway. So I'm like 1 big M, one space big M. So then still somebody comes up, they'll spell O-N-E. Like, no. So yeah, so I'm trying, but there's 10 bazillion ways they apparently answer the word 1. All right. Anyway, so good. So everybody put 0.75. Yeah, right. That's it right there. So you would take 3 moles divided by 4 liters, sorry, and that's going to be equal to 0.75 big M. Or you could also do another way to get this wrong, or to get it wrong on canvas anyway, moles per liter. That would be right as well. All right. That's just the unit. And notice often, because chemists are that lazy, mole, and you've seen this before in a lot of your homework, will be MOL. MOL. Not uncommon. All right, good. So there's that. Now let's take this up just a little bit of a notch. And instead of doing it this way, let's say you've got 9 grams of H2O in 0.5 liters of water. Molarity. Wait, what? Hold on. I tried to make that super easy. It makes no sense at all. you have water in water, the molarity is going to be a pretty good trick. All right, there you go. 9 grams of sodium chloride. I'm trying to do it so you didn't even really need a periodic table there.
Jim, did I not get it right?
Wait, hold on. I have to calculate this myself here.
Okay. Wait, don't forget my answer.
That is not right.
I realize now that it says grams, not moles.
Yes, that says grams, folks. Yep. Yeah, Jeremy, that's what I got. No, that's not right. You've got 9 grams of salt and half a liter of water. What's the molarity of your salt, aqueous salt solution? So convert the moles first, and then divide by the volume. So how many moles would 9 grams of salt be? Mackenzie, good. Kaya, good. Remember, divide in to find moles. Divide in to find moles. So it'd be 9 grams divided by the molar mass of salt divided by the number of liters. Yeah, no, that's right. Chris, that's right. Huh. All right, guys, I guess we'll go over this. Okay.
No, Jim, I know what I'm doing. I know what I'm doing wrong.
Okay, good. All right, guys, so we got 9 grams. We need to convert this to moles. So the molar mass of sodium chloride is 35 plus 23, so it's 58. That comes to, don't turn off on me. That comes to 0.155, so I'll say 0.16. 0.16 moles. Sodium chloride, not a whole lot. So you're going to take 0.16, divide that by 0.5, and that equals 0.31. 0.31 molar, or 0.31 moles per liter. do another one of these. That seems shakier than I was hoping. Let's do another one of these. All right. Maybe I should have deleted that from the board. You might still be writing that down. Sorry. No, can't. There. All right. Let me give you another problem here. See if we can. All right. So Pepsi has 44 grams of sugar in 0.355 liters of, we'll say, water. Now sugar is C11, actually C12. Nope, sorry, C6, H12, O11. So what's the molarity of Pepsi? Those are real numbers, by the way. Look at the back of a can of Pepsi. I think I messed up that. My formula for sugar is not right, but that's okay. Yeah, it's C12H22O11. That's okay. Use that formula. That's why I'm not getting the numbers I'm expecting to get here. Yeah. Noah correct. Lath correct. Mackenzie correct. And that's it. So if I didn't say your name, you might want to recheck this. Something's gone awry. Yeah, Kaya, good. That's correct. Jeremy, good. All right, guys, I'll give you the answer in a second here. If you guys are having trouble with this, I would really, really, really recommend going back in your homeworks and doing some of those molar mass problems and finding just the basic moles. Just finding the molarity of something should be pretty straightforward here. I'm adding a small piece. So if there's problems here, and I'm seeing a lot of what looks like probably, just silly mistakes, well, silly mistakes are going to cost you points. So I'd go back and practice this. All right, guys. So the molar mass of whatever that molecule is, because it's not sugar. The molar mass of that was 260. 260. We're going to take that and divide that by how many? Wait, sorry, I made that around. We'll take that by 44 grams. Divide that by the molar mass, which is 260. And that comes to, check my calculator here. That comes to 0.16, actually 0.169, 0.17. That's how many moles of sugar we have. Remember, moles, you guys measured that out. A mole of sugar was a lot of sugar, right? It was a huge amount of sugar. So you guys measured that out. So this is only going to be, so it's only 44 grams, so it's not nearly that much, but it's still a lot of sugar to drink in a drink. So then we're going to take that and divide that by the amount of liters it's sitting in, which in this case is 0.35 liters. And so that comes out to 0.47, 0.48 actually. Big M, or 0.48 moles per liter. So if you had some trouble with that, okay. Yeah, that's a big molecule. I could certainly see that being a trouble with the molar mass. With C6H12O11, that's a big molecule to calculate. I'm willing to bet that was several of the problems I saw was that one. So, and which is why I tend not to put that on quiz or exam questions, because of it's easy to make a poor mistake on that one. Yeah. So, for example, not giving you the correct formula for sugar. All right, guys, good. All right, so hopefully that's pretty straightforward. If you guys are having trouble calculating those moles, if you have to think about it, frankly, practice those some more. That horsey should know how to move. So if you have to go, how do I do this again? Practice those some more. I guarantee your final grade will be much happier if you don't have to think about how the horsey moves. That horsey, that should be your pawn, frankly, at this point. That you should know how to move that. All right. Good, you guys. All right, so that's molarity. We're going to do some problems with molarity, of course, in homework to practice that a little bit more. So that'll be coming at you soon. Hopefully, by the time you're done with that, it'll be pretty straightforward. It's just moles divided by volume. Sometimes the volume's different, as we'll see in this little lab we're about to do. They use a different volume, but it's the same idea. There's another idea out there called molality, which we're not going to be doing in class, but it's very simple. It's just how many grams divided by liters. And that's molality. So I'm not going to spend time on that, because when you guys won't remember that. When you guys get to college, they'll teach you that again, and you'll be like, oh, well, this is a piece of cake. So I'm not going to spend time with that, because it's very, very simple. It's just grams divided by liters, and that's molality. But the tougher one is molarity. So I wanted to introduce you to that a little bit. And again, it's not that tough. Okay, good. So I want to show you a couple of things here. Let's have some fun with our acids and bases. So let me stop sharing. Good. All right, let me get some stuff out of my way, although you guys will be back. Okay, this is pretty fun. Watch this. All right, so also hold on a second. One more thing before I do this. All right. So what I want to do here now, in fact, before I do this, let me go back to the whiteboard a second. Neutralization. hold on, that's neuralization. That's a whole different thing. There we go. Neutralization. There you go. All right. Now, this word was mentioned last week in that video I showed you. Remember the one with the computer graphics from 1986? So, but we didn't spend much time on that. I want to spend a little bit more time on that today. So neutralization is when an acid and base basically cancel each other out. So they're neutralized, just like the movies. We need to neutralize the enemy, sir. That's what we're doing. We're neutralizing. So when acid or base gets together, they will neutralize each other. They will balance each other out. All right. Now, before we get much deeper in this, let's see where you are with understanding these concepts. So, what is the definition of an acid? What is the definition of an acid? What is the definition of an acid?
I have this somewhere. I'll find it.
So Mackenzie's correct.
Wait, I didn't hear the question. I was typing. What was the question?
What is the definition of an acid? There you go, Jeremy. That's correct.
I just had electrons in the brain for some reason.
Yeah. Well, it is chemistry. It's wise to have electrons on the brain. Yeah, that's right. And what is the definition? Kaya, I will give you that, although it tends to be broader than that. But that's okay. I'll give you that. And James, that's a characteristic of an acid. I'm looking for the definition that I gave you last week. The definition of an acid.
Oh my God. I found in my notes, I have like the title on the top of the page, just like acids and bases, and then just a big hole, and then the characteristics.
Leif, that is correct. And James, that would be more the definition of a base. Although that's not the definition that I gave in class, but that is correct. But that's not the definition I gave in class. All right. So the definition of an acid, be very thankful that we're not quizzing today, because you would bet this would be on the quiz, you guys. Ooh. All right, next week though, there'll be a quiz next week, I guarantee. So the definition of an acid is a substance that donates protons. The definition of a base then was what? What's the definition of a base? Kenzie, good. Chris, good. Yeah, good. There we go. Oops, actually, Chris, the other way around. Sorry, not that letter, but the other one. James, good. There you go. Kaya, good. There you go. Yeah. Good. So if an acid donates protons, a base accepts protons. Well, not necessarily, no. I mean, sometimes that's true, but sometimes it's very willingly, especially if they're mixed with an acid. They very willingly. All right, good. So we keep talking about protons here. Now, in the rest of the year, we haven't really talked too much about protons, except at the very beginning, we've been talking about electrons. So this is kind of weird. We're talking about protons. What does this really mean? When we're talking about protons, what are we really talking about here? Jeremy, good. Yeah. When I'm talking about protons here, what am I really talking about when it comes to acid-base reactions? The acid donates protons, what? And base accepts protons, what? What am I really talking about here? Mackenzie, good. What does an acid really do? And it's the telltale sign that something is probably an acid. And the other thing is the telltale sign that something is probably a base, although not always. Not always. Well, what we're talking about here, gang, is we're talking about hydrogens. Talking about hydrogens. All right, and why are we talking about hydrogens? Because a hydrogen, remember, if I Bohr diagram the hydrogen, it's this. You guys have ever read Watchmen? There it is. If you guys have ever read Watchmen, which frankly I don't recommend. It's very, very good, but it's a little intense. But if the guy, what is his name, Dr. Manhattan or whatever, I forget what the guy, the big blue guy, he's got this tattooed to his forehead because this is hydrogen. Look him up. I forget what his name is. He's the big blue guy in the watch. He's got that right smack dab on the forehead. Why is that? Because that's the ultimate atom, right? Hydrogen is the ultimate atom, and his skill is he can manipulate atoms. So he's only a superhero in the Watchmen, as a matter of fact. He actually has superpowers. Anyway, so that's why he's got that tattooed to his forehead, is because remember, all atoms really come from hydrogens in the stars. The hydrogens smash together and form heliums, the heliums smash together and form this, that, and the other thing. That video, next thing you know, you've got the entire periodic table up to at least uranium.
Yeah, he's called Dr. Manhattan.
There it is. Thank you, Dr. Manhattan. Yeah. Read that. By the way, that comic is no longer even close to being appropriate anymore. It never really was, and it certainly isn't now. Anyway, so sorry, just thinking about it and being a little bit disgusted. But so he's got this thing tattooed to his forehead, and that's why that's true, because this is a hydrogen. But what happens then if, so it's basically one proton and one electron, right? This is the ultimate atom. So what happens when you remove this guy over here? Well, two things happen. One, it becomes a positive one, because it's got one proton and no electron, so it has a positive one charge. And two, it becomes just a proton. That's all there is. So when we talk about donating protons, what we're really saying here, almost all the time, and especially in high school level chemistry, what we're saying is we're donating hydrogens. So if you think about this as really meaning a hydrogen plus, that is not incorrect. Right? And usually, although not always, and it's even in high school level chemistry, this is not always true, it accepts protons. And usually this means an OH. Usually that means an OH negative. This is called a hydrogen ion. This is called a hydroxide. You better know that. This is a hydroxide ion, right? We've studied that for months and months.
What about like OH3? Like the hydronium or whatever.
Right, hydronium, that's right. OH3, that's a positive ion. OH3 is just an H2O that's got this attached to it.
All right.
So very often in chemistry, and really usually what happens is you get this H3O, actually, that would be that. Because this H positive tends to not just hang out freely in the solution. It has a tendency to attach itself to a water. And so you get this. But depending on the chemistry teacher and the chemistry website and the chemistry video, you'll see it either like this or you'll see it like this. But they tend to mean the exact same thing. Yeah. All right, good. So if I were to try to find my acid base here, oh, before I do this, hold on. What is the definition of a strong acid? What's the definition of a strong acid? And or a strong base, for that matter. What makes an acid or a base to be considered strong?
There's just gaps in my notes wherever you're asking questions, I swear. Literally,
That's a good thing we're going over this again, though, isn't it?
literally says at the bottom of the notes, it says a strong, and then it just stops. Like,
Were you
that's-
falling asleep last week?
no, I think I was behind. I think I forgot to take notes, and then I was like, oh wait, I need to take notes. And so I just filled in the bottom part that you had, and then it got erased, and I was like, oh yeah, whatever. I probably won't need it.
Gotcha. Yeah, this is so hard online, you guys. All right, so let me see. So Kaya, I'll give you that, although I would look for a little bit more in the full answer. But you're basically correct there. Jeremy, that's absolutely right. Mackenzie, absolutely correct. Good. Yeah, what makes, so James, what would make an acid have a low pH? Low pH, again, would be a characteristic of a low acid, but that's not why an acid would have a low pH. And that certainly wouldn't be the characteristic for a base. Good. All right, guys. So to fill in Noah's notes. All right, James, that's better. That's better for an acid. Right. Okay. So a strong acid / base is a substance that completely disassociates into its ions. So an acid or a base will completely disassociate into its ions. Oops, wrong its, sorry. Just default to that its. All right. So what does that mean? Completely disassociates into its ions. Well, this is one of the videos that I showed you, actually this, 2 of the videos I showed you last week. We had HCl, hydrogen chloride, right? We had HCl, which is composed of 2 ions, a hydrogen plus and a chloride negative. When you get them together, you put them in water in an aqueous solution, they break up completely into their ions. These things completely break apart. Sodium hydroxide would do the same thing. This would be a base. When you put them in, when we'll put them in water, Na+, OH-, they completely disassociate into their ions. Okay. A weak acid or a weak base doesn't do that. I showed you that other video last week that had the big, looked like the big black eggs with the little, the little white things next to them. And if you remember right, they were floating around in aqueous solution, and the big black eggs would deposit their little white hydrogens on the water, and then they'd come back a little bit later and pick it back up. All right. But if you watch the video, they didn't all disassociate. Some of them had their little black, that had their little white, their little hydrogen stuck to them, and some of them didn't have their little white hydrogen stuck to them. Some of them get rid of them, and some of them took it back. So they did not all completely disassociate, right? And that would be vinegar. Even though vinegar has a low pH, it's a weak acid because it doesn't completely, acetic acid to be clearer, it doesn't completely disassociate water. Now, when these guys get together, what happens, right? Well, when they get together, they have a tendency to have little dance parties, right? So we have these little H's right here that are wandering around, and across the crowded dance room, they're both, the H and the OH are hanging out, and they're both just drinking their punch in the corner, and they look across the dance room, and the crowd parts, and the H positive sees the OH negative just standing there, and their eyes meet for just a little bit too long, and they slowly approach each other across the dance floor, and next thing you know, da, 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 true love, right? So what do they make? They make H2O, right? Then we get these other guys, which to be honest, we don't really care about. In an acid-base reaction, we don't really care about these. These guys are called the spectator ions, and you'll see this in a second. But in this case, just to let you know what's happening here, and we already know we did this last week, although apparently not with everybody. All right, so these guys get together because they're again positive and negative, and they again go la la la, and they form a wonderful relationship. And that's why we have salt on this side, NaCl, which is specifically table salt in this case, and H2O. Now notice what happened. Which one of these things donated the proton, aka the hydrogen? This guy did. So that's the acid. That's the one that put the proton into the solution. If it wasn't for that, there wouldn't be a proton, right? So that's the acid. It's the one that donated the proton. This is the base because it's the one that accepted the proton. It accepted the proton. Here, I'll take that. Okay, so that's the base. So you've got H plus and OH. You've got H2O. All right, good. And the book talked about the intermediate, which is the H3O, but it's the same thing as this. It's just an extra one that then gets rid of when it wants to become OH. So it's just a slightly more complicated step. All right, got that? All right, let's do, give you a slightly more difficult one here. If I did this, which one of these? I'm going to kind of make this easier to see what's happening here. This wouldn't necessarily be the reaction. All right. So don't necessarily worry about this side, although it will give you some hints. But on this side, which one is the acid and which one is the base? Which one gives the proton? Which one is going to accept the proton? So which one's going to be the acid? Which one's going to be the base on this side? On the reactant side. Whenever you're asked this question, always look at the reactant side. Conjugate bases, conjugate acids, which I'm not going to touch again, or the other side. But Mackenzie, good. Kaya, good. So which one's the acid? Which one's the base? Jeremy, good. Good. This one's a little weird, isn't it? That's why I'm giving you this, because it doesn't really follow the rules that I've given you. There's no OH here, is there? There's no hydroxide ion here. So you need to take a look at this side and say, oh, look who takes the electron. Look who takes the proton. Oh, so that must be the base. All right, guys. So in this case, this is going to split up how? It's going to split up to HO, H plus, and an H plus over here, and an SO4, -2. That's the ions that this would divide into. Okay. Notice this is a strong acid. This is a sulfuric acid. It's a very strong acid. It actually donates 2 hydrogen ions to the solution, although that doesn't always indicate it's a strong acid. So I haven't focused on that. But in this case, this is a strong acid. And in this case, this guy's going to divide up into, actually, it's going to stay NH3 as a matter of fact. And this hydrogen over here is going to go, hey, NH3 is weird. And if you guys remember biology, remember the amino group, remember those? This guy will accept a proton. Just kind of does. He's kind of happy to do it. So this guy goes, woo. So there's kind of like, this guy's like, well, you're kind of attractive. And you're like, well, you're kind of attractive. So kind of makes a little heart. A little, at least for a couple of nights, maybe, I guess, for a week or two. So anyway, so they get together and they form NH4. But how would you know which is the acid or the base? Because this has an extra hydrogen on it. So it had to accept one of these. bases accept the protons. Usually we can say bases accept the hydrogens. So since this accepted the hydrogen, this had to be the base. The other clue here is what is the charge on these hydrogens? They're negative. How do you know that? Because they're on the opposite side of the equation. They're on the right-hand side of the equation. Everything to the right-hand side of the equation is going to be the negative anion, the negative ion. So these guys right now are carrying a negative charge. These guys are going to be carrying a positive charge. So these are the guys that are going to be the protons. They're going to donate the proton. Okay, that was a little harder. That was a little harder. All right. All right, guys, good. So that's basically how that works there. Oop. Whoever donates the proton is going to be your acid. Whoever accepts the proton is going to be your base. Depending on the problem, sometimes it's easier to look for the acid. Sometimes it's easier to look for the base. Now, one more thing. We talked about neutralizations. Let's talk about that a little bit more. All right. So let's say before. So before, I'm going to say I've got a huge container of base. So I'm going to say I've got a huge container of base, which means what? And it's a strong base, which means I've got a lot of hydroxide ions floating around. That's a strong base. And these hydroxide ions can't wait to no longer be hydroxide ions. And they will do a lot to make that happen. Last week, you saw it eat an aluminum can, right? They're like little teeny tiny piranhas, right? They can't wait to make things happen. So this would definitely be a big old base in here, right? All right. So now what would happen if in my big old base, I can kind of draw this, I start to pour in an acid. All right. So this acid is going to have a whole lot of hydrogen ions. My base is going to have a whole lot of hydroxide ions. You can bet I'm going to have something relatively exciting happen here. Now, it's not always very exciting, but something will definitely happen here. This is a reaction that can't wait to happen. You guys did this a couple weeks ago when you mixed acetic acid, vinegar with baking soda, base, and you saw a whole lot of bubbles. And if you were able to take the temperature of it, you would have felt it got a little bit warmer because it was releasing heat. So there was something happening there. Not all acid-base reactions are that exciting. Some are even more exciting to the point of deadly. So, but here we go. So what's going to happen here? So if I go before and now I go after, like all those wonderful diet ads, right? So now what am I going to make in here? Well, once we're done, we have an H2O, 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 H2O. So all of those H's are going to pair up with those OH's, and they're going to form H2O molecules. They're going to be neutralized. Those hydronium ions will have all found mates. Those hydrogen ions will have all found mates. And next thing you know, we got a rocking little disco party over here. Nano, nano. Nano, nano. Right? Okay. And of course, true love. You know, my wife and I should get remarried, and I'll hang a big H around my neck, and she'll hang a big OH around her neck. And we can meet across the. Anyway.
What does hydroxide look like in real life? Like,
What does it look like?
Like, yeah, what is like the physical?
Like that?
That. No, like to actually look at like water or oxygen.
I mean, are you looking like for the space filling molecule or?
Yeah, like if you actually had a bunch of OH in like a bowl.
Like if you fill the cup up with OH, what would it look like?
That. I mean, you couldn't. I mean, it would look like a base. I mean, you.
Oh, like with your bare eyes, like just looking at it.
Yeah, like color, consistency, things like that.
Could you do what you just showed right now? Or you
No.
just
No, because these are highly reactive. OHs and Hs are highly reactive. So you couldn't hold it in your hand. I mean, literally this would be what we call the perfect acid or the perfect base, and it would eat through anything more than likely. So you'd be hard pressed to have just a bucket of OHs floating around. You couldn't do that. It would react with the oxygen in the air. It would react with the hydrogen in the air. It'd probably be bad. So yeah, OHs are usually in some sort of a salt like NaOH attached to an ion of some sort for NaOH. Hydrogens are usually attached to something as well, H2HCl, H2SO4, HNO3, something like that. So you wouldn't have a bucket of hydrogens just floating around. Even hydrogen gas is H2 gas. The hydrogens attached to one another. Yeah. So I can't tell you that because I don't think anybody knows. All right. All right. So these guys get together to form the dance party and everybody's happy. So this would be a neutralize. This would be after. This would be neutralize. Okay. Because this is no longer an acid and this is no longer a base. This is water and more than likely some sort of a salt floating around, depending on which acid base you met together. Those leftover ions would be floating around as well. NaCl in the case of our hydrogen chloride sodium hydroxide experiment that we keep talking about in the exam. Okay, so that's neutralized. Now let me show you a couple of things. Make this fun. So what I've got here. Oh wait. Let's stop sharing here. Unless somebody needs me to wait a second, I'm going to stop sharing. Now, what I've got here is this. This is red cabbage. Red cabbage, you can totally do this at home. It's so easy and it's really kind of cool. I just took red cabbage and I boil it. I put it on the stove, I let it cook for 10 minutes and I turn it off and that's it. And then I take the liquid and I pour it out. That's all there is to this. This is like $2 and some cents at whatever grocery store you shop at. No need to get the organic stuff. All right, so I'm gonna pour this in here. Oh. I hope this still works. And we'll have to see what happens. That has changed color about me. I'll see if this works. All right, cabbage juice is theoretically an indicator. Back to the notes. An indicator, you may already know what this is a solution that changes color in the presence of an acid or a base. I presently have no idea how this is about to react because I'm not too sure what I'm looking at here. This should be a beautiful purple color. I think it went bad on me over the weekend, which I don't understand. Usually takes it a year, and even then it still works. It just smells really bad, and stuff loves to grow in this. So if I forget to empty this out and I put it in my shed and come back to it a year later, oh, that's a pleasant surprise. You can bet how I know the answer to that. All right, so if everybody's got that down, so that's an indicator. So cabbage juice, cabbage juice is a type of an indicator. It changes color in the presence of an acid or a base. Let's see if we can make this work. So what I've got right here is ammonia, which even though it's NH3, it doesn't have that telltale OH, doesn't have that telltale hydroxide. We saw a second ago that it is indeed, it acts like a base. It will accept the proton. I'm going to take some of this lovely smelling stuff. make something happen. Sure. This might be a little bit more exciting than I was planning on. Let's see. Bad idea, but we'll do it anyway. You're really not going to work for me. Oh, no. Oh. What happened? I really don't understand. Many colors change here. I'll tell you what, let me. I should have turned a glorious green color. Boy, oh boy, oh boy. I've never had this happen to me. I'm sorry, you guys. I try it in the presence of an acid, see if this works. I'm not betting it will. Nope. That should change by now for sure. So it's not. Well, nuts. That is very disappointing. Sorry about that, you guys. That's the first time I've ever had that happen. I don't know what happened. Yeah, I'm a little at a loss. What happened there? It's disappointing. Darn it. That's so pretty too. Nuts.
So it's
Yes.
cabbage juice and you added an acid?
Yeah. Yeah, it was cabbage juice and I added a base at first and it should have turned a bright, beautiful green. Because the more base it gets, the more green it turns. It's very, very pretty. And then here, let me see if I can find my picture of this. At least I can show you the picture of what was supposed to happen. And then when you add a base to it, it gets redder and redder and redder. And it's very, very pretty and it's very cool. And I'm not finding my little thing too. I don't want to spend too much time looking for it. Here. Thanks, you're my hero. There. All right, here. All right, take a look at that's what was supposed to happen, you guys. It has this beautiful purple color, not this ugly brown color. This beautiful purple color. Mine was even purpler. It was even pretty. And then as you add an acid to it, it gets slightly more and more and more and more red as you put an acid to it. A strong acid is going to be a bright red color. So when I put in all that vinegar, it should have been a bright red color. On the flip side, a strong base is going to become this beautiful. It's actually on mine. It was more of this color. It was beautiful green color, it turned more and more and more and more green as it headed towards the base. So that's what that's what an indicator does. It changes color in the presence of an acid or a base. That's what should have happened. What I wanted to show you here is a brief titration experiment. So I wanted to put in a little bit of base so that it turned green on us. And then what I was going to do is add a little bit of acid and a little bit of acid and a little bit of acid and a little bit of acid. And as I added in the acid, it would have gone from probably a 12 or a 13 solution. And then it would have, as I added a little bit of acid in, a 10, a 9, an 8, it would have slowly but surely changed colors back to the purple color. And the reason for that is because my base was being neutralized. Just like the picture I threw on the board a second ago, that base would have all those OHs in it. I would keep continuing to add H's in the form of acetic acid. And as I did, those OHs would be neutralized, 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 neutralized. So that base solution would become more and more and more neutral, more and more and more 7, until they all have dance partners and everybody's dancing with everybody. So they're no longer angry because they're all dancing and having a good time. So they're neutralized, right? So that would be when we got to the pH of 7. Now, if I continue to add acid to it, well, now I'm adding a whole bunch of things to it that no longer have dance partners. So then we would go from a 7, and then we would continue to get more and more and more acidic until I could have gone all the way to probably a 2 with this vinegar. And that kind of thing from there. So that's a neutralization experiment. Start with a base or an acid, it doesn't matter. Start to add the opposite one. You start to add the opposite one, and as you do, you basically form dance partners. You're forming water, right? Which I think we talked about this before, but if you look on the internets and find all these wonderful ways for all these natural cleaners, which I'm sure was very popular for Earth Day, and there's nothing wrong with the idea of natural cleaners, but most of the recipes are silly because it's add baking soda and water, and well, now you know what you get. You get salt water, so it's not really an acid or base cleanser. Yeah, strong bases do have a tendency to react with metals, and we saw that happen with the aluminum. And almost all strong bases will react with aluminum, and most strong bases. So aluminum is very eager to react. It's very easy to have aluminum react. So if we had almost any strong base or any strong acid, actually, Kaya, we would have seen that reaction. We would have seen different products, but we would have seen it eat the aluminum. Yeah. So nothing necessarily special about the sodium hydroxide that we saw last week in that video. We would have seen that happen with other strong bases as well. Yeah. Just quite a while. Yeah. So look out for bases, in other words. Good. All right, you guys. Since that failed miserably, let's go to the next thing I had in mind for you guys. Anyway, so what I'm going to do is I'm going to give you guys a website here, and I want us all to navigate it together, and we're going to work through this together because there's some great stuff here. Let me get some stuff off my screen if I can. Yes, go away. All right, and then bring this up here. Whew. All right, cut this, and I'm going to put this in the chat for everybody. There's that. All right, guys, click on that, and I will share my screen for you so you can see what you should be looking at. Assuming this works for us today. I have never had cabbage juice go bad. I am flabbergasted. I must admit. What's the first? Huh. Oh, well. All right, you guys, let me know when you're there. You should all be looking at this here.
Like, should we let you know with a Y or just tell you?
Yeah, sure. Let me know with a Y, or let me know, or somehow let me know that everybody's there. All right, guys, good. All right, when you're here, go to Quick Start. No need to log in. Just hit Quick Start. Titration level 1. Quick Start titration level 1. So far, only 4 people have let me know that they're there. Hopefully, everybody's here. Okay. So you should now be here on this page. All right. Now I'm going to click here, click here. All right. Now don't go anywhere here yet. Everybody should be here on this titration screen experiment, the contaminated stream. Suddenly sounds like a Hardy Boys mystery. All right, the contaminated stream. Now what I'm going to do is I'm going to play this video. You guys don't play it, because if you do, you're going to hear it twice or 3 times or whatever it is. So don't play the video yet. You will have to play like a second of it before you can hit next, but don't play it yet. Let's watch this together.
Wait, it says I have to like sign into the website. Do I need to do that?
No, just do Quick Start.
Oh, but when I... Oh, never mind. Let me do it. I don't know what was wrong with it.
Yeah, okay. Yeah, I should just be able to hit Quick Start. Okay.
and it worked.
Good, good, good. All right. So we're gonna watch this video together, and please, something that I want to this. I feel like I'm on a kindergarten field trip here. Don't wander off. Okay. So I really do want us to go through this together, and the reason for that is you can zip through some of these pages, and if you go all the way through it, yay team, you did it in 5 minutes, yay for you. But the problem is I really want to show you some stuff on these pages. This does a really, really nice job showing you a lot of the stuff I've been talking to you about today, and really gets deeper into what a titration experiment is, how it works, and it also gives you some experience using lab equipment that I'd like you to get some experience with this year as well. So this does a nice job with a lot of the things that I would have liked to have given you this year. So please follow along, and we'll get through this, and it's kind of neat, I think. Anyway, all right, here we go. So watch the video first.
Breaking news. There has been an accident involving a lorry carrying over 1,000 litres of hydrochloric acid. It is feared that some of the acid might have leaked into a nearby river upstream of a site of special scientific interest. Chemists are at the scene to assess the damage and work out how acidic the river has become. When an acid, for example hydrochloric acid, is mixed with water, it completely dissociates, producing a solution of hydrogen ions and chloride ions. Acids can be neutralized by substances called bases. Bases that are soluble in water are called alkalis. When an alkali, such as sodium hydroxide, is dissolved in water, it completely dissociates, so that all of the sodium ions and hydroxide ions are dispersed randomly in the solution. An acid and alkali react to form a salt and water. For example, sodium hydroxide and hydrochloric acid react to form sodium chloride and water. If we draw the dissolved compounds as ions, we can simplify the equation, leaving out the sodium ions and the chloride ions. They are known as spectator ions because they appear on both sides of the equation. When we have removed all the spectator ions, we are left with the net ionic equation, showing just the hydrogen ion and the hydroxide ion reacting to form a molecule of water. A concentration of a solution tells us the amount of a substance dissolved in a volume. It is measured in moles per cubic decimeter. We can determine the concentration of hydrogen ions in an acid solution by performing a titration experiment.
So right there to stop it, this is exactly what I was attempting to draw for you on the board a second ago. This would be a base solution, chock full of hydroxide ions, just waiting to react with something, probably very, very angry, and can't wait to get its hold on something like a bunch of hungry little piranhas.
As the acid is added to the alkali, the hydrogen ions react with hydroxide ions to form molecules of water. The end of the
So see, as he's pouring in, or she's pouring in the hydroxide, the hydrogen ions, they automatically get together with the hydroxide ions and they form little dance partners, right? So there you go. That's why the neutralization experiment is like a giant dance party.
titration is when all of the alkali has reacted. At this point, the pH is neutral. We use an indicator compound which changes color when the point of neutralization is reached. In this example, the balanced equation shows that 1 mole of hydrochloric acid reacts with 1 mole of sodium hydroxide. The amount of alkali can be calculated using the known concentration and volume of the alkali solution. The volume of acid that reacted can be read from the burette. It's good practice to repeat the titration and calculate the average volume added. We can now rearrange the equation to calculate the unknown concentration of acid. As part of the environmental response team, you will have to act quickly to assess the environmental impact of the acid spill and advise on an appropriate response to protect the site of special scientific interest. Samples from the contaminated river have been collected and transported back to the laboratory ready for you to test. In this activity, you will learn how to set up and run a titration experiment to calculate the unknown concentrations of acid in the samples collected from the contaminated river. You'll need to carefully add just the right amount of acid to the alkali solution to reach the neutralization point and judge when the indicator color changes.
All right, guys, good, good, good. So we're going to do that. So you might need to play a couple of seconds of the video just to make sure you can do it, because otherwise it won't let you move on, because Dr. Patel here is very, very picky about making sure you do things right. So once you do that, feel free to hit next, hit finish, and just keep clicking until we get to this page here. All right, guys, give me a Y in chat when everybody's at this page here. Good. All right, guys. Good. Now I said there was no quiz today, but I was partially lying because this is a small quiz, but it won't go on your permanent record, so don't worry about it. Now I want you guys to do this, see if you can get all 5 right. And the way this works is you click and drag these things into their boxes is the way this works. So give yourself a couple of minutes, see if you can get all 5 of these right. Feel free to hit check when you filled in all the boxes. Should be able to get all these right. And then give me a Y when you're done. There's a couple of people looking like they wrapped that up there. Give me a Y when you're done there. There we go. Good, good, good. Hopefully everybody got what?
So I'm a little bit ahead, and there's a big word, and I don't know what it means.
And don't go ahead, please. Please don't go ahead, you guys.
Okay,
Follow
I'll wait.
along with me, because otherwise you're going to miss things I want you guys to see. All right, thanks. All right, like the big word, for example, and I want you guys to see. All right, so hydrochloric acid. You guys stay with me, everybody. All right, good. So hydrochloric acid is absolutely fully dissolves because it is a strong acid. Acid and alkali reactant, it's called a neutralization reaction or a dance party in science gym. Its indicator helps us to see the point of neutralization. The whole point of a indicator is to see when it equals that 7 pH. 7 pH is totally going to be neutral. And last but not least, the whole point is to find the unknown concentration of an acid, knowing the known concentration of a base.
So Jim, I'm gonna go grab some water. I'll be right back.
Okay.
Just letting you know.
Good. All right. So we're going to check that. We're going to do clickety clickety click and get you guys to this point. This is very, very simple. Feel free to do this. Let me show you how to do it. Sodium hydroxide, you're going to pick what's the pH. That's wrong, by the way. That's not what I wanted to do. Hydrochloric acid, pick what the pH is. Water, pick what the pH is, and go from there. So once you're done there, this should be quick and easy here. And then hit check. Hopefully you got that right. I'm sure you did. And then go from there. All right, guys, I'm going to hit check myself here. Next. Then the next thing here is pick which one of these are acids and pick which one of these are bases. Now, these are fairly straightforward acids or bases. They have the telltale signs that I've told you about, especially the bases do. So pick how many of these, there's more than one, pick all the acids. Pick all the acids. Good, guys. So hopefully these KOHs, these OHs are certainly going to scream at you base, 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 base. So in that case, boop, boop, boop. Yours might be in a different order. I think they change the order every time. But hydrogen chloride, nitric acid, sulfuric acid are going to be your acids. Ooh, oh, I'm right. Let me tell you something here real fast. This is probably where you were, Jeremy. Let me tell you something here real fast. This will help you with this. This is called phenolphthalein. This is a type of indicator. It's an indicator that when you start, it's a pink color. When you finish, or when you hit the end point, and the end point is that 7, that neutralization point, it turns clear. This is the indicator we're going to be using for the rest of this experiment. So now that you know that, answer these 3 questions. Read them kind of carefully. One in particular is a little tricky if you go too fast. So it turns from pink to clear when it's neutral. And when you're done with that, give me a Y in the old chat box. Remember, please don't go ahead. I know it's tempting, but please don't go ahead.
Sorry, what does alkaline mean exactly again?
Alkaline means basic. Also means you're not on the page that I'm on. Oh, no, okay, never mind. All right, alkaline means basic. This is a base. All right, guys. So the phenolphthalein indicator is not affected by the pH of the solution. That's false, because that's the whole point. The phenolphthalein indicator changes color close to the point of neutralization. That's absolutely right. That is the point of an indicator, is to change color. When adding acid to the base, the phenolphthalein indicator changes color from colorless pink to at the end of the titration. That is not right. It goes from pink to clear, from pink to clear. That's false as well. All righty, right. Boop. Moving on. Boop. 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 Okay, now try this. Try this. I'm not going to tell you much about this. See how you do. But you can drag and drop these things over. And notice your scale. Got a tare button on your scale. And see if you guys can get this to be about 1 gram. If you go a little bit above, in fact, I've had students who get it exactly right, and it doesn't seem to want to take. So you might want to get it to 1.02 or 1.05. And let me know, put a done in chat, because there's so many Y's now, I don't know which Y is which. Put done in chat when you're done with this. This one's a little bit tricky, not too bad. I'm willing to bet you won't get it right on your first try. But if you do, good. If you don't, that's okay. All right, guys, looks like a couple of you guys are done. A little hint, don't forget the tare button. You don't want to weigh the weighing boat. So hit the tare button.
Wait, I got to read 1. I'm supposed to tear after I get to read 1. I'm confused.
You want to tear it after you put the weighing boat on, because you don't want to weigh this.
I did do that.
Yeah, there were students in another class, if they got it to exactly 1, it didn't work. So put a little bit more in and see if it'll take it. I think the instructions are wrong. You want it to be slightly above 1, as a matter of fact. Did you get it, Jeremy?
Yeah. I had to do 1.02.
Yeah. I think the instructions on this are not accurate. I think it really wants extra. All right, guys, good. I'll do this myself here. All right. Oh, Chris's did work exactly at 1. If some students seem to work at 1, and I don't understand what the determining factor is on that. But so it looks like you guys are basically done. I hope. All right. Yeah, this is one of the things. This is using a scale. Remembering that you don't want to weigh the weighing boats. When you put the weighing boat on there, you hit tare, so it automatically cancels that out. You don't have to do any subtraction and introduce error. And then from that point, you just fill it up to where you need. In this case, we're okay to be 10% off. So we can actually go to 1.1 as a matter of fact on this. And here we go. Let's see if we're done with that. So now we have weighed out the sample, the solid sample of sodium hydroxide. Now, solid isn't going to do us a whole lot of good. Most solids don't react with other solids. So we want to make a solution of this. And this is where we come to our molarity. So in this case, we want to put it in exactly 250 centimeters cubed. Centimeter cubed is equal to a milliliter. 250 centimeters cubed of liquid. Relatively simple here. All you're going to do is just squirt water in there. But there is a trick to this. So let me show you something before you do this. Let me show you, because I want to introduce you to the idea of the meniscus, which some of you who were with me in middle school might remember the meniscus, but I'm sure everybody could use a review. So I'm going to put this in here like this. Now, notice what's going to happen here is there's a line right here on this flask. That's indicated by this line right here. So now I want to go slow. So I'm going to do one big one here. If I remember right, I can do one more big one. There. Well, that's too high, but I can still show you what I want. See this curved line? This is the line of the liquid. It's curved. We call this the meniscus. MENESCUS, if I'm not mistaken, and I might be. But this is the meniscus right here. To get this right, you read meniscus, menisci from the bottom of the meniscus. So this bottom should be directly on this line right here. And then you'll get this. So I'm going to hit check. It's going to say I failed miserably, and I'm going to do it all over. And you got to be real picky on this one. Dr. Patel is very picky with his volumes. There, I think that's right what I want right there. So try that one, you guys. This is the meniscus, measuring volumes, creating exactly 250 cubic centimeters of liquid. All right, when you're done with this, give me a done in chat, please, so that I know everybody's good. Give me a big old D or big old done. D-U-N. Thank you, Jeremy. Thank you, James. Or give me a big old Brooks for Brooks and Dunn. For the few and the proud country western stars out there. Good, you guys. All right, good. It looks like most people are not having trouble with this. This is good. This is giving some other classes a couple of fits here on this one. Because you really got to nail that exactly, which is why I'm telling you that. Otherwise, this gets frustrating here. And why I wanted us to go together. So now we have a concentration of sodium hydroxide, don't we? We have a molarity. We know the mass, about 1 gram. We know the volume, 250 cubic centimeters. So from there, we could figure out the molarity, which we're going to do eventually. So I'm going to go next, next, next. Now this is just figuring out the molar mass of sodium hydroxide, which we would need to do to find the molarity, right? So in this case, all you're going to do is type in the molar masses for sodium, hydrogen, and oxygen. Take a look at the periodic table. I'll give you a tip on this because this is European. It's upside down, apparently. So, the top is the molar mass. Molar mass of sodium is 23. Right. So the top is the molar mass. And you can type it in too, by the way. This should be quick and easy. So we're figuring out the molar mass of sodium hydroxide. All right, guys, we got one person who's done out there. Anybody else? So 23, 16, and 1 is what you want to type in there. Oh, okay, Mackenzie. Very fun, Jay. Yeah, remember, read from the bottom of that meniscus. And that meniscus has to be just absolutely pixel by pixel on top of that line. Read from the bottom of the meniscus. Oh, if you're doing it on a phone, yeah, that might be very, very tricky. And don't forget the bottom of the meniscus. So the bottom of that curve is what you want on the line, bottom of that curve. All right, guys, I'm gonna keep going forward a little bit here.
What if you use a hydrophobic glass? Would the meniscus then be on the top?
Yes, probably would be. If you use like Teflon, yeah, that probably would be. Yeah, good, Mackenzie. Good. Now this one is just, they just have you actually figure out the formula that you're going to use. So we're trying to figure out the amount of substance in moles, which we've done this 1,000 times. This just makes it confusing. They give you this little tip right here. So what do we want to do? We want to put the mass divided by the molar mass. They want to basically find, we're looking for moles. I wish they would do this differently than they do this, but we're looking for moles. So how do you find moles? You take the mass that you have divided by the molar mass of the object. So the mass that we have divided by the molar mass of the substance. So we're just creating the formula here. So just put mass over molar mass and then hit check. That should take you forward. Oops, sorry, I shouldn't hit check. Sorry. Put mass over molar mass. Put mass over molar mass and then hit check. But don't go off of that page yet. I want to show you something on this page. So mass over molar mass. Okay, Chris. And then notice when you're done with that, mass over molar mass, then you hit check. It does the calculation for you. When it does the calculation for you, it does your mass, and these are all going to be a little bit different. I got 1.05, but your numbers might well be different. So it's 1.05 divided by 40 grams per mole, right, which is the molar mass of sodium hydroxide. So it's just finding the moles, which you've done a bazillion times. Piper did it earlier today. So we're only using 1 gram, so our moles are going to be pretty stinking small here. So it's 0.0263 for me. You're going to be a little bit different if you have a different mass, and there's nothing wrong with that at all. In fact, I think that's kind of neat. This program allows you to do that. Okay, so I'm going to hit next at that point. Now this one's a little bit trickier. It's asking us to find the concentration. Now the concentration of the molarity, I told you earlier today what molarity was. So what is that? That's going to be moles, the amount of substance, moles, divided by volume. Moles divided by volume. But because we're using decimeters, instead of just using liters, we're using decimeters cubed. We need to put this 1,000 in here. So that 1,000 is just to convert to decimeters cubed instead of the centimeters that we measured with originally. So, so don't worry too much about that. But once you've got this going on,
1,000 decimeters. Why would that be decimeters?
Because if you look, it's DM, right?
That's less.
Right.
Oh, instead of, okay.
Yeah, I wish they just measured in moles here, but we have such a small amount of substance. If we did it in pure out straight centimeters cubed, we'd be dealing with pretty small numbers. So. This just makes it a little bit easier to work with. All right, guys, has everybody got this? So in the numerator, you've got amount of substance times 1,000. And in the denominator, you've got volume. So in the numerator, amount of substance times 1,000, and the bottom, you've got a volume. This is just the formula we're going to use to find the concentration, to find the molarity of our substance. All right, guys, I'm not too sure. Not getting everybody chiming in here, so I'm going to kind of sally forth here. Now the idea is just to do that formula that we just put on the board. So we need to find out our concentration. Right. So we just kind of follow this. Our concentration is going to be 0.11. We're going to take the amount divided by the volume. There we go. These numbers might be slightly different for you because you've got different masses, but it should be something like this. Basically, the smallest number, put it on top. 250, which will be the same for all of us because that's the volume that we all measured. 250 cubic centimeters in this case. And it should be 0.1 something for all of us. I'll pause here for a little bit. Good, you guys. Yeah, feel free to throw me a done in the chat there. I'm not sure where folks are. Remember, I do want us to stay together here, guys. I know it's tempting to sally forth, but do stay together, please. Thank you, James. All right, guys, I'm going to click the old thing here. All right, moving on to the next. Now we can finally start preparing for the actual titration / neutralization experiment. All right. Now let me show you this one. This one for me was the trickiest of all of these because I didn't see something. So I'm going to tell you this so that way you can see it. When you're at this page, what you want to do is click this up arrow and it slowly fills with liquid. And notice when you get about halfway through, look at this. See this little arrow here? This little refresh arrow basically is what this is. It shows up when you're at about halfway through your pipette. So I'm going to leave that there. But once you get that, you click on this arrow and then you can basically finish it off from there. That makes sense, but that's tricky. So if you go too far, the arrow disappears. And I kept going too far and I never saw the stupid arrow. can finish this in time. All right, folks. And this does this little shaky thing. So what we're doing with this is we're cleaning out this pipette, making sure it's nice and clean. Then you dump the excess in this pot over here. And then you're done. Yeah, fill it about halfway full. Keep a careful eye on that rotated arrow. And then go from there.
I'm sorry, how do I do this again? It's not working for me. I can't
So you put that pipette, I shouldn't hit check. You put that pipette in there. And then you just hold down on the up arrow until it's halfway full. Hold down on the up arrow. And then when it's about halfway full, you should see this little symbol here, this rotate arrow symbol pops up between the up arrow and the down arrow. And then you should be ready to go.
Okay.
Did you get it?
I got it.
Good.
Yeah.
Good.
And then I move it into the waste beaker.
Yeah. And just move it to the waste beaker. Hit the down arrow. It'll spit everything back into that beaker. And then you're done from there. All right, everybody got it? All right, guys, going to move on here. Of all of these windows, I'd say that's the trickiest of all of them right there. So now we just cleaned out our pipette. Now the next thing we're going to do is we're going to make a solution of our base that we're going to titrate into. This is fairly straightforward. We're just going to grab a hold of this. Again, this is going to be the tricky part here, is getting it exactly on that meniscus so you get it just right. So hold down on the arrow. It's also tricky because it fills very slowly through the thicker part and then very fast to the thin part. So chances are you're going to blow this the first time you do it, and that's just fine. And slowly, slowly, slowly. Again, the bottom of the meniscus. I think I got it right there. Getting the timing right on this one's a little tricky because it goes really fast once you hit the thin part. And then once you're done, you're going to drag it into the conical flask and hit the down arrow. And you'll be, well, and then put a couple squirts in. Then you'll take the indicator, put a couple of drops in. And then you're done. And then we're almost ready to actually do the titration. We're almost there. This is all the lab techniques that you guys will need to know when you get to do real labs with real flasks and with real pipettes. All right, folks, give me a Y or a done or an X or a you got it or whatever you need to do in chat to let me know that we're ready to move on to the next one. Good, guys. Whatever you need to do. All right. Now we'll get to this point here. Now remember, the whole point of this is we're trying to find out what's going on with this river. We are looking for an unknown concentration of acid. We're using a titration method to find the concentration of acid in this river. So this is where the spill was, this big triangle right here. We got B and we got C, right? We'll see how far we can get with this. Right now, we're just going to click B because that's how much acid is in the river at this B site. So click on B. And watch very carefully. Let's see if we can whiz through this because this is pretty simple. So just watch me for a couple of seconds and we should be able to whiz through these next few ones, right? So just watch me. First thing you're going to do is take this, move this up like that. Take this, fill this over here, and just squirt for a second. And then that's all there is to that. So keep watching. The next one, you put your funnel in here and you pour it in like that. So what we're doing is we're cleaning out this pipette, making sure there's nothing in this pipette but this acid solution. And then the next one, close the pipette, close the valve, pour water in there, or pour your acid solution in there, take your funnel out, hit check. There. Oh, and the last one, just take your eyeball and put it right across from the meniscus. So you're reading it at eye level. All right, guys. So meet me here. Go ahead and do all those things. They're really quick. And then meet me here. Give me a Y when you're on this page, because there's several things I want to explain to you on this page. So meet me at this page. All right, guys, looks like 3 of us are here. Be sure to give me a Y so I can keep going here. A Y or a done or a something. Because this is the page I really want us to go through together, because this is what I really want us to do. Everything else was good too, to get some practice with lab technique. But this is really the key to this. All right. Now, what we're about to do is do an actual titration. Well, virtual titration at any rate. So first thing we need to do is we need to put in our initial reading. How much fluid is in our pipette? Each one of us is going to have a different number here, so you can't necessarily go by what I'm doing here. But let me show you a couple of tips that'll make this easier for you. First off, notice this pipette reads backwards, 9, 10, 11, right? It goes down. Yours might have different numbers than mine, but it reads down. The other thing to notice is each one of these lines represents a tenth. So this is 9.1, 9.2, 9.3, 9.4. What Dr. Patel wants us to do is, if it's right on the line, read that as a 0. If it's off the line a touch, read it at 0.5. Now, this program gets a little picky. What it wants is a 0.5. What it wants is a 0. So you might need to experiment a little bit with that. But the other thing you must do, significant figures. He wants everything in 0.00. So even like right now, mine is a 9. It's a 9.1, 2, 3, 4, 5, 6, 7. I'm going to type in 9.70. Whoops, where'd my 9 go? 9.70. So everything, significant figures, needs to be to the nearest hundredth. Needs to be to the nearest hundredth. So you guys do the same thing. Try to read this. Remember, you're reading upside down. A lot of people forget that. And each one of these represents a tenth. And if it's halfway between, you can go to 0.5. So you have 9.75 or whatever you might be. All right, guys. So give me a Y in chat or a done or something when you're already there. Good. Yeah, a little bit of practice reading graduated cylinders. Remember to read from the bottom of the meniscus again. A little bit of practice reading graduated cylinders. This is a big, big skill that your first lab in college, you will be going over this, I guarantee. This is not the last time you'll hear the word meniscus. This will be back. So I'm giving you a little bit of experience with this, so that it's not brand new material for you when you're at college. All right, Jeremy, very good. It's funny, you and James are doing the same thing. That's very funny. All right, only 2 people appear to be done, or at least you're indicating you're done this to me. Good, James. This one's a tricky one.
I'm sorry, one more time. Can you explain exactly how to get that number?
All right, so, and here's the help reading the barrette too. So if you see this, notice you read from the bottom of the curve, the bottom of the meniscus, the bottom of the meniscus. In this case, so 11, 11.1, 11.2, 11.30. Don't forget to go to the nearest hundredth. They want 2 points after the decimal point. Now here, notice it's between the 1 and it's between the 2. So it's 21.15 in this case. So if yours is between, now sometimes Dr. Patel is a little funny. That's the name of the guy. I don't know if you caught it at the beginning, but that's the name of this feller. I'm not just making that up. Is a little picky. So if it seems like it should be 21.1 and you're like, well, what's going on? Try 21.5 and see what happens. Or if it looks like 21.5, try 21.0 and see what happens. And you can only go either 1, you can only go 0 or 5. You can't go anything else here. You got it now, Noah?
Yeah, I got it.
Good. All right, you guys, let's sally forth here. Next. So now we're actually going to do the first actual titration here. So watch me first, because this is going to help you out a lot if you know what you're doing. I'm going to hit start. Now, the acid is pouring into my base. We're having a dance party. H's are meeting up with OH's. They're chatting a little bit. They're going out for coffee. Next thing you know, it's wedding bells. But here we go. So when this thing changes, this is that phenolphthalein, the solution. When it turns clear, I'm neutralized. So I'm watching carefully. Oh, almost, and right about there. Okay. So you guys do that same thing. When it turns clear, hit stop. When it turns clear, hit stop. And give me a D or a Y or an X or a P or a Q or something in chat to let me know you got that. So just about to the point where I can let you do your own thing on this. But I found this goes a lot smoother if I walk students through this step by step. And I think they get a lot more out of it. So. Good, guys. And then once you're done with that, feel free to hit check. And then next. Then the next thing you're about to do is just start filling in the chart. You're just going to start filling in the chart. Now, before you do that, let me tell you something, because I'm going to just let you go. I bet you we'll be able to get this done if I just let you go here a little bit, because we're getting late. But what you're about to do, this first trial you did was what I call the rough trial or the sloppy trial, because it was fast. You just let it pour in there until it changed color. Completely inaccurate. The whole point of the rough trial is to save time, because now you have some idea what volume of acid you need to add to your base. You're going to see in a second with its first and second accurate titrations, you're going to do it drip by drip by drip by drip. And if you were to try to do it without having any idea where your neutralization point is, it would take you all day in the lab to go drip by drip by drip by drip by drip. So you do the rough titration first to give you some indication of what that volume is. So that now you're going to do 2 more of these after this, and they're going to be closer to the real answer. So I'm just going to kind of go through this on my own. You guys go through this on your own. The explanations are fairly self-explanatory from here on out, I think. All right, looks like one person's done already. I just finished mine up. And if you finish, go ahead and start doing the second accurate titration. Feel free to just keep going here. There's like a couple of people done with the first one. Good, good, good. And once you're done, just go straight to the second one. Not sure we're going to be able to get everybody to finish, but I do want to show you a certain endpoint here. So keep going as far as you can. Good, Chris. Yeah, keep going. Once you got the first one done, go ahead and do the second one as well.
Should we still stay when we're done, or what should we do?
Yeah, go ahead and finish this. Have you done the second titration as well?
No, when we've done the first one, should we stay when we're done, or just keep going?
Start to the second one. Go to the next one. And once you finish the first titration, start the second titration. All right, guys. Then when you finish the second titration, meet me here. Meet me at this window here. And we may not have time to have everybody finish, so I might just call this and have you guys pay attention to me for a second, but give you a couple of more minutes to do as much as you can. I think a couple of people are pretty much on target here. I've now done this like 8 or 9 times, so I might be a little quicker than you all are. Good, you guys. All right. And I've got the next board completed for you guys. So when you guys get to this point, feel free to put in here what's in the next board.
So my brain is kind of turning off. How much longer does this take, the
We're almost there.
activity? Okay,
Just keep
cool.
going. Almost there. Really, once you finish that, we're done. I do want to show you one more thing here. So we're almost done. We're just about to the point where we can start to compare our concentrations. All right, guys. And just put this into this window here. Your numbers might be different than mine. They probably will be, but you know, the smallest one, the biggest one, kind of, you know, the closest one to these numbers, use those. Your numbers will probably be different. All right. I'm gonna hit next. Kind of zipping through these last bits here. All right, folks, watch the screen here. Let me just do this with you guys. And we'll wrap this up at this point. Feel free at home to finish this up. That's absolutely fine and cool. But I just want to make sure we're all to this point and I can let you guys go without being too late, because I know it's been a long Monday morning. So what we just did here is we figured out the concentration of acid by doing a titration experiment on 2 points of this river, at point B and point C. The first time you did that experiment, you used the point B water. The second point, you used the point C water. You saw that there were different volumes of acid needed to neutralize the base that you used. With a few calculations, really just molarity calculations, you were able to figure out the concentration of acid at B and the concentration of acid at C. So this last part here is just taking a look at what happened here. So if you take a look at A is a normal pH. It's 7. The pH of the river is 7. After the spill, the pH of the river is 0.9, highly, highly acidic. At point C, the concentration of the acid is 1.1, still highly acidic. At point D, we go downriver a little bit more. It gets a little bit better, but still acidic, 4.7. It's perfect for Earth Day, right? So now we answer these questions here. The pH of the river is normally neutral. That's true. That's told to us by the 7 at point A. The pH decreases as the concentration of HCl decreases. That's just what acids do. The lower the stronger the acid, the lower the pH. The site of the special scientific interest at C here is good. Well, it's at 0.11. Good is 6 to 0.9. It ain't good. In fact, it's bad. So that's a big old false right there. And last but not least, the pH of the river returns to a moderate level by the time it reaches site D. Site D, it's 4.7. Moderate is 4.6 to 5.9. So indeed, it is moderate at site D. So we would say true there. Boop, boop, and we're done. All right, guys, I'm going to leave you there. I've got some extra credit possibilities for you guys this week. This titration experiment has 3 other experiments that go with this website. I'd love for you guys to do that. I'm not going to assign it, but it's really good experience with this. It's really good way to get to know a very important way of doing chemistry, but I'm going to give you extra credit on that. So for every one of those that you do, it's worth 3 points of extra credit. And if you do all 3 of them, it's worth 10 points of extra credit, which is a full assignment or half a quiz. So it's fairly beneficial for you guys to do that and spend the time on that.
So
Now that-
I just want to make sure that this can't decrease our score, right? If we go for the extra credit, like that's
Oh,
how
no.
that's how
It
you
can
have
only
it.
increase. It can only increase. That's why it's extra credit. It can't count against you. Yeah, it's extra credit. So, so you did the first one. The first was the longest one because you had to learn a bunch of stuff. It's shorter after this. It also shows you the other neat thing about this is it shows you why this is important. Here you were able to figure out the pH of a river, which is certainly an important thing. And the next one, you're going to figure out whether or not aspirin are any good, or perhaps they're slightly poisonous. And the next one, you're going to figure out whether or not hairspray or a hair product is actually, it's coming in from foreign lands, and we're not quite sure it's really safe. So this is the FDA type of a thing right here. And I didn't even do the last one, so I don't know what that is. But a variety of ways where chemistry is actually not just something you do in a lab book and something for assignments, but it's actually ways to practical chemistry. So if you have the time, I'd recommend doing that. If you don't, that's okay. That's why it's extra credit. I'd recommend doing that. But bottom line, if you have the time and you were a little fuzzy on the molarity problems, you might want to go back and practice your moles. I would recommend that first before you do the extra credit. All right, you guys. All right, any questions before I let you go?
Nope.
All right, ladies and gentlemen. I will see you all next week, where we'll get into the gas laws and entropy. Ooh. All right, you guys. See you next week, everybody. So long for now, and have a great week.
Okay, thank you. Bye.
Bye, you guys.
Thank you.